Hello? Yeah, it's better now. Can you hear me?
Yeah.
Okay, good. So today we're going to have the talk by Professor Avrim Blum. And Avrim Blum received his BS, MS, and the PhD from MIT in 1987, 1989, and 1991, respectively. He then served on the faculty in the computer science department at Twodimensional University from 1992 to 2017. In 2017, he joined the Toyota Technology Institute at Chicago as chief academic official. Professor Blum's main research interests are in theoretical computer science and machine learning, including machine learning theory, algorithmic game theory, algorithmic fairness, and the non-worst-case analysis of algorithms. He is currently working on fairness and incentive issues in machine learning systems that know when they don't know, and the robustness guarantees in presence of adversary attacks. He has served as program chair for the IEEE Symposium on Foundation of Computer Science, FOX, the Innovations in Theoretical Computer Science Conference, ITCS, and the Conference on Learning Theory, CORD. He has served as chair of ACM, SIGACT Committee for Advancement of Theoretical Computer Science and on SIGACT Executive Committee. Blum is recipient of AI Journal Classic Paper Award, the ICML called 10-Year Best Paper Award, the Sloan Fellowship, the NSF National Young Investigators Award, and the Herbert Simon Teaching Award, and he is a fellow of the ACM. Let's hear his talk on learning in presence of biased data and strategic behavior. Please.
All right. Thank you. Thank you. Well, it's great to be here virtually, and thank you. Good morning. Thank you all for coming. So yeah, I am going to talk about learning in the presence of biased data and strategic behavior, and different parts. I'm going to talk about two things, and different parts are joined with Saba Ahmadi, a postdoc with us, Hedya Behagi, also a postdoc with us, Kazia Nikita, one of our PhD students, and Kevin Stengel, also one of our PhD students. So let me get started. Okay, so I'm going to talk about two things. The first one has to do with fairness and biased data. And this is from a paper that we wrote called Recovering from Biased Data. Can fairness constraints improve accuracy? This is with Kevin Stengel in Fork 2020. So let me start with the one slide version of this talk, this part. So there's been a lot of interest in fairness in machine learning. And usually when we talk about it, we think of a trade-off between fairness and accuracy, or maybe between different fairness constraints themselves. But what if we are in a situation where our training data is somehow biased? That can happen sometimes, and is one of the things that could produce a biased classifier. And a question we ask is, could fairness constraints actually lead to improved performance, even if you just care about accuracy? So normally, if you have an optimization problem and you add constraints to it, this is not going to improve your solution. But if you're optimizing the wrong thing because your training data is biased, then maybe those constraints could actually lead you in the right direction and get you to a better solution. And this is motivated by work of Kleinberg and Raghavan on similar questions in ranking and Hart-Price cerebro fairness notions that I will define shortly. What we will do here is posit some simple bias scenarios and then examine whether existing fairness notions might help or hurt accuracy in these scenarios. Okay, so let me start to kind of the high level for fairness. So algorithms are increasingly being used to automate or advise decisions that impact people. And this can be things like whether to be approved for a loan or not, whether to be admitted to college, whether to be hired for a job, bail and parole decisions. And it would be a big problem, I think it's universally agreed, if these algorithms were systematically biased against some racial, ethnic, or gender group. And in the research community, I think this really came to the forefront through this example of an analysis of the software called Compass for predicting recidivism, meaning going back to committing more crimes, that was used as an aid in bail and parole decisions. It takes candidates for bail or parole and classifies them as being a low risk for committing more crimes, for recidivism, or high risk. And an analysis of this data, and I think this analysis was in a particular county in Florida, this was shown in ProPublica by Larson et al. And it examined Black defendants and white defendants, and it showed that looking through the data, that Black defendants who were not rearrested within the next 2 years had been nearly twice as likely to have been classified by the software as high risk compared to their white counterparts, 45 to 23%. Whereas on the flip side, the white defendants who were rearrested within the next 2 years had been labeled low risk almost twice as often as Black defendants. As Black defendants who were rearrested within the next 2 years. And if you kind of to put this in machine learning terms, let's think of a person as an example, and let's call them a positive example if they are managed to, not commit more crimes and not be rearrested within the next 2 years. And let's call them a negative example if they do get rearrested within the next 2 years. Okay, so that's a positive and negative example. And let's think of classifying someone as low risk as predicting that they are positive, and classifying them as high risk as predicting that they are negative. If we think of it that way, then this first bullet is saying that the false negative rate, the fraction of positive examples who are misclassified as negative, is twice as high for the Black defendants as the white defendants, whereas the second bullet is saying the false positive rate, the fraction of negative examples that were misclassified positive, is twice as high the other way around. So that seems problematic. Now, shortly after that, another study came out by Flores et al. In the Federal Probation Journal. They said, well, on the other hand, Compass is calibrated. Of those it calls high risk, there's about a 75% rearrest rate across both groups. And of those it calls low risk, there's about a 30% rearrest rate across both groups. And what's happening here is it just depends on which way you take the probabilities. This is saying the probability of the true value given the predicted values are approximately the same, but the probability of the predicted values given the true values are not. And so following this, there was a lot of kind of discussion and debate about, well, is it fair? Is it not fair? What do we mean by fair? And this led to, I think, a lot of really interesting work defining various notions of fairness that one could then try to analyze. And so that's what I'm going to do now, is just kind of talk about, what are some things that we might want in a machine learning based classifier. So let's think of something positive, not going to jail and committing crimes. Let's think about, let's say, an applicant for getting into college. Sure.
Yeah. So first is like the probability, the true conditioning on prediction. What does that mean? Is true mean the ground truth stable? Prediction is the prediction of
That's right. So what fraction of the people who were labeled high risk actually were found to reoffend within the next 2 years? So and what fraction of the people who were predicted, classified as low risk, reoffended within the next 2 years. So that's kind of the truth given the prediction. So out of all the ones predicted one way, what did the truth look like?
Okay, I see.
Yeah.
Yeah.
Good. So I think this will be, I'll give some examples here that I think will make them more clear. But I'd rather think about, let's say, getting admitted to a college or getting hired or getting a loan. Okay. I know. So the one notion called equality of opportunity, and it was proposed and analyzed by Hart, Price, and Cerebro, says, we'll say a predictor satisfies equality of opportunity with respect to a set of groups G if the probability you predict positive, given that it really is a true positive example, if those are approximately the same across the groups. So the way to think about this is that if you know that you would be a good student or a good employee, or you would be a good borrower who would pay back the loan, you should have about the same chance of being predicted positive, namely being admitted to the college or hired for the job or approved for your loan, regardless of whether you belong, which group you belong to. And so that's the notion called equality of opportunity. Another notion, also by Hart, Price, and Cerebro, called equalized odds, says we want that, and we also want the same thing over the negatives. That if you would not be a good student, borrower, or employee, you should have the same chance that you're not admitted, hired, or approved. Okay. And just to be clear, it is possible to satisfy this. There are some trivial ways. So for example, if you predict everyone positive, like let everybody into your college, that would work. If you predict everyone negative, you don't let anybody in, that would also work. If you predict everyone randomly, so each applicant has a 10% chance of getting in regardless of how good they are, that also would work. But those are a little kind of silly. But importantly, by predicting correctly, if you could really correctly determine whether a student would be successful or not, whether an employee would be successful or not, a borrower would successfully pay back the loan or not, and correctly output it, that would indeed satisfy both of these conditions. Okay, so those are two conditions. Let's continue. Another is called calibration, and this is the other way around. A predictor is calibrated with respect to a set of groups if the probability that you're a true positive given that you predict positive, and the probability you're a true negative given you predict negative, if those are approximately the same across groups. Okay, and the way to think of this is that the meaning of predicting positive or negative should be about the same regardless of the group. If it predicts positive, that should mean, I don't know, there's a 75% chance you're really positive, and that should be the same across the groups. Okay, that's what it means to be calibrated. Okay, and the last one is called demographic parity, and this one, a predictor satisfies demographic parity with respect to a set of groups if the probability you predict positive, if that's about the same across your groups. So there's nothing about the truth here. So this is saying that if you're going to admit 10% of the applicants from group A, you should also be admitting 10% of the applicants from group B. That's called demographic parity. So these are various notions, and you can kind of discuss them and some of their properties, and many of them can be in conflict with each other. You'll notice that calibration and equalized odds are related via Bayes' rule, and if the denominators aren't the same, you can't satisfy both. And so anyway, they can be in conflict as well, and a lot of sort of discussion and debate about that. So what we're going to look at here is the ability to address bias training data. So a commonly cited reason for bias in classifiers is the idea that often training data can be biased, and that could get reflected in the classifier you learn from that data. And so what we're going to do here is, rather than arguing about which fairness notion is sort of right or morally better, let's just look at natural ways training data might be biased, and we'll see if these constraints could actually improve the accuracy of the classifier produced, or maybe make it worse. It'll give us a way of kind of concretely, measuring what's going on by looking at how these affect accuracy. And we're going to do this through some theorems, but you could also imagine doing this empirically too. And if some of these constraints improve accuracy, that would give additional motivation by saying, look, if you have biased training data, this notion could really help, reduce your error rate. And so just to be clear, so we're going to do this through some theorems where we're going to make a bunch of assumptions like you do when you try to prove theorems. And some of our assumptions will be realistic and some will be less realistic. And it'll be on both the bias and the ground truth target function. So I'm not going to claim that the assumptions I'm making are, that's very completely general. They're going to be very specific. So it's just, but they will allow us to actually analyze what's going on. And I think there's plenty more that one could do here. Okay, so let me say the setting we're going to look at. We're going to imagine two groups, and we'll think of A as the advantage group and B as a disadvantage group. So all the bad things are going to be happening to group B, and that's what we're going to try to fix. So here are our two groups, A and B. Our groups are disjoint. Membership is observable. You can tell whether someone belongs to group A or group B. We're going to be doing binary classification, things like who gets approved for a loan, who gets hired, who gets admitted. To be clear, we're not trying to tell whether someone comes from group A or group B. That's given to us. We're trying to decide who gets approved for a loan or admitted to the college, that kind of thing. So like here's a picture showing binary classifier. I'm going to use these red lines to denote a classifier. It doesn't have to be a linear separator. It's just a generic classifier. I'll think of the blue points as the positives and the green points as the negatives. There will be some true distribution, dA on XY pairs. X are the examples, Y are the labels for group A, and some distribution dB on XY pairs for group B. They might be different, so the optimal classifiers for the two groups might be different. Our overall distribution over people will be a mixture with 1 minus R on dA and R fraction on dB. That's the R is telling you the fraction of the population that's in the disadvantaged group. And our algorithm is going to be just doing ERM, which empirical risk minimization, which just means minimizing training error over our family of hypothesis class, our family of classifiers, on a training sample, possibly subject to fairness constraints. That's what we'll be looking at. And I'm going to be thinking of everything in the large sample limit, which means I am not going to be worried about generalization error, overfitting, and all those sorts of things that much of machine learning theory worries about, and they're extremely important. But I'm going to be imagining we have as much data as we want. It just happens to be biased, and not worrying about those issues. It certainly would be interesting to look at those issues too, but we're not going to. Okay. So now let me tell you the bias models. I'm going to formally define a couple of bias models we'll be looking at, and then we're going to just formally define a bunch of things. I'm going to be giving a bunch of notation, but don't worry, you're not going to have to remember the notation. I just give it. I will say what everything is when it comes up. So the first form of bias we'll be looking at we call underrepresentation bias, and the idea is that your training data is not representative. Why? Because people in group B are not showing up in your training data to the extent that they will later. And moreover, that rate might differ for the positive and negative examples. Okay, so if the blue points are the positive examples, say for group B, some of these blue points just, they didn't show up. So why might that happen? Well, it might be that your organization hasn't been friendly to people in group B in the past, and so members of group B don't apply. And it could be that the positive examples in group B, they're well qualified, they have more other things they can do, and so if you haven't been friendly to them, they're just not going to show up in the training data. Whereas maybe the less qualified members of group B, they have fewer other choices, so they still show up. And so what ends up happening is that your training population for group B just looks more negative than it really should, because a lot of the positives are just not showing up. So that's what we call underrepresentation bias. And so formally, the model is you draw a random example from the overall distribution. If it's an example from group A, you keep it. If it's from group B, if the label is positive, you keep it with some probability beta plus. If the label is negative, you keep it with some probability beta minus. And beta plus might be much smaller than beta minus. That's the case I was talking about. But don't worry, you don't have to remember these betas. But that's the model of underrepresentation bias. Okay, another similar at the high level, but technically different, is what we call labeling bias. Here, everyone shows up, but some fraction of the positive examples in group B are mislabeled as negative in your training data. So each one, may be mislabeled with some probability new, mislabeled as negative. That could happen if your data was labeled by people who had a bias against, folks in group B. Maybe didn't treat people in group B as if they were as qualified, and so mislabeled some of them as negative. So if that happens, again, your training data is going to look more pessimistic for the members of group B than it should. Okay, so formally the model looks like this. You draw a random labeled example from D. If the example X is in group B and the label is positive, with some probability new, you switch the label to negative. Okay, that's what we call labeling bias. And then we could think of both of them together. And then again, we'll be looking at this in the large sample limit. Okay, so those are the specific bias models we'll look at. They are very stylized. I'm not claiming that this is the real way bias happens, but they're interesting to think about. Okay, so the next thing I have to tell you is the assumptions we are making on the ground truth classifier. Okay, so that's the blues and the greens here. So first of all, guiding principles. I want there not to be a perfect classifier. So you'll see here that this red line, those are our Bayes optimal classifiers. Those are not perfect. Otherwise, underrepresentation bias is just going to be less interesting in the large sample limit. Another is that the Bayes optimal classifiers, I'm going to set things up so they satisfy all the fairness conditions we talked about over the true unbiased distribution. Because I don't want to create an intrinsic conflict where one of them is just inherently going to hurt because it's not satisfied. I want to set things up so they're all satisfied, so we can really analyze, them on a kind of a clean way. So, given that, here's what I'm going to assume. We're going to assume that there exist Bayes optimal classifiers. That's these red lines. HA star, that's this one, and HB star, that's this one. In some family, capital H, maybe it's linear classifiers, maybe it's something else, such that they're not perfect, but their errors are uniformly distributed. Okay, so what do I mean by their errors are uniformly distributed? I mean, if for any example X, what I want is that there is a probability 1 minus eta. So eta is going to be something that's less than a half, but probably 1 minus eta that the true label equals what H star says. So if this is the positive side of H star, and this way here is the negative side of H star, that the true label agrees, it's blue, and if you're in the positive, with probably 1 minus eta, and is the opposite with probably eta. So basically think of each of these points with, if say eta is a quarter, with a 75% chance is blue and 25% chance is green, independently all these points. And on this side, each point, 75% chance is green, 25% chance is blue, independent of those points. And same on this side too, on the A's. Okay, that's the assumption about the ground truth, that these Bayes optimal classifiers, that they're not perfect, but their errors are uniformly distributed. Every point is an equal chance of being, 75% chance it agrees with that label, 25% chance it doesn't agree with the prediction. So the other thing I want to assume is that for both groups, there's a probability mass P above the line on the positive side and the 1 minus P on the negative side. So if you remember, this is a statement that these H star A and H star B satisfy demographic parity. So I'm setting things up so the Bayes optimal classifiers, HA star and HB star, satisfy demographic parity. They classify a P fraction of points as positive. I'm not saying that a P fraction of points really are positive, that the fraction of blues, I'm not saying that's P. I'm saying the fraction of points above the line is what's P. Okay. So these are Bayes optimal classifiers according to the setup so far. You'll notice that I've defined things, so these classifiers are calibrated, meaning that conditioned on saying positive, there's a 1 minus eta chance they really are positive. Conditioned on saying negative, there's also a 1 minus eta chance They really are negative. That's the same for group A and for group B. So I've defined them to be calibrated. And they also satisfy equal opportunity and equalized odds. We can run Bayes' rule here. The probability that it says positive conditioned on being positive. So in other words, this guy here, calibration, is saying, given that you're above the line, what's the chance you're blue? This one here says, given that you're blue, what's the chance you're above the line? So what is that? Well, given that you're blue, what's the chance you're above the line? Well, we can just run Bayes' rule here. There's a p probability you're above the line, and conditioned on that, there's a 1 minus eta chance that you're blue. And the denominator, the same thing, plus there's a 1 minus p chance you're below the line times an eta probability you're blue. And so that's the probability that you're above the line, given that you're blue. And that's the same for group A and for group B. Okay, so I just wanted to set things up so the Bayes optimal classifiers satisfy all the conditions we talked about. And now we're going to say, all right, let's add the bias into the data and see what happens. Okay, so that's what we're going to do now. So let's see what happens with underrepresentation bias. And so let's think of beta minus as 1. So all the negatives in group B show up, all the green points, but we're going to start reducing beta plus from 1 down to 0. And that means the blue points, we're going to start getting rid of them at random. So let's just start removing some blue points at random and seeing what happens, okay? So if we do that, what happens is ERM, minimizing empirical error, is going to still do the right thing. It's still going to produce your HA star and HB star until this beta plus gets so low that there are actually more green points above the line than blue points, more negatives above the line than positives, in which point it's going to say, you know what, I'm just going to classify all of group B as negative. I'm still going to do the right thing on group A, but I'm going to classify all of group B as negative. Okay, so if you really got that bad, you know, that would be not fun if you're a member of group B, because it's like nobody from group B is getting admitted because, you know, even the Bayes optimal classifier can't do better than 50%. You know, there's not even more than 50% positives on the positive side. Okay, so what about calibration? What would calibration do? Well, calibration, it turns out, will actually even make things worse. If you start having some points blue points not showing up, what does calibration require? It requires that the probability you're a true negative given you predict negative has to be the same for the two groups. What does that mean? It means below the line, there should be the same fraction of green points. But notice, below the line for the Bs is more green than below the lines for the As because we got rid of some blue points. And the only way to fix that is to add some more blue points on the B side because there's no way to fix that on the A side. And so the only way to fix that is to actually raise this line, making the world harder for people in group B. And on the positive side, what it's saying is, hey, what fraction of blues are above the line? And that's actually higher for the A's than the B's. And the only way to fix that is to lower this line here to equalize. So the above the line, the ratio of blues to greens should be the same for the A's and B's. If you notice what's happened, I don't know how I added there. What's happened is we've just started discriminating against the B's and discriminating in favor of the A's by allowing less B's in and more A's in. And if we don't care about that, our accuracy has gotten worse because we're trying to match probabilities that are in this biased training data, and we're forcing them to be reflected in the classifier. So calibration is forcing the classifier to reflect the biases in the training data and will make things worse. Now, demographic parity kind of does the opposite. If some of these blues don't show up, then because the ones not showing up, there's more above the line not showing up than below. To get a p, remember there's a p fraction here, but now there's a less than p fraction above the line here because we just removed a bunch of points above the line. So that'll force us to lower the line. Now that'll be helpful for group B. People in group B might like it. We're going to admit more, but it's reducing accuracy. So the decision maker is not going to be too happy about that. On the other hand, equality of opportunity and equalized odds they allow HA star and HB star to go through. They don't require moving anything because the probability you predict positive given you're a true positive and on the negative side, those haven't actually changed. And the reason they haven't actually changed is, what are they saying? The probability you predict positive given you're true positive, that's given that you're blue, what's the chance you're above the line? Well, we assumed that some of these blue points didn't show up, but whether they showed up or not was just a function of their true label, blue or green, not a function of whether they're above and below the line or not. And that means that the blues who show up, the chance you're above the line is the same as the blues who didn't show up. We haven't changed that at all. So if random blues don't show up, the blues that do show up, still the same chance they're above or below the line as before. That hasn't changed. So these constraints don't force you to move away from the Bayes optimal classifier. But even more than that, what they do is it turns out that they lock these two classifiers together. And they make it so that these are really the only optimal classifiers subject to that constraint, no matter how small beta plus gets. So even if you start, getting rid of more of these positives so that ERM would like to classify all of B as negative, it can't do that, satisfying quality of opportunity, unless it classifies all of A as negative as well. And unless the parameters are so bad that the classifier wants to just classify everybody as negative, nobody gets in to college at all, then the only way it can do the, right thing on the A's is to also do the right thing on the B's. And so that will cause the Bayes optimal classifier on the A is going to help you lock in the right answer on the B's. So it'll keep HA star and HB star being output even when ERM would like to do something crazy. It would like to just throw out all the B's. And so that's nice. So equality of opportunity will maintain the algorithm producing the Bayes optimal classifiers. Okay, let's go on to the next model, which was labeling bias. So labeling bias. Yeah.
Can I ask a quick question? So
Yeah.
it's like, you actually train these two groups separately. It's like you get HA for group A and you get HP for group B.
Yeah, we're imagining that the family of classifiers allows you to completely separately pick one function on the A's and another function on the B's. And so what ERM does is really the family of classifiers is pairs of separators, one for A, one for B. If you don't like that, if you say, you know what, I want to force you to use the same classifier for the A's and the B's, then you can still do the same thing by just imagining that we live in a high enough dimensional space, right, that it's possible to distinguish the A's and B's, and our classifiers are flexible enough to do whatever they want on the A's and separately whatever they want on the B's.
Yeah, I see.
So, yeah.
I see.
But I'm just think of it as just completely separate. Yeah.
Okay, thanks.
Yeah, I guess maybe it's a good time to mention that it is important. This issue really is most important when you're imagining that the right thing to do is actually different on group A and group B. If you really believe that A and B had the exact same distributions and the exact same Bayes optimal classifier, then one way to fix this bias model is to only train on the A's.
I see.
So you could say, you know what, I'm just going to ignore all the B's, train on the A's, and use that classifier if I think that really that'll still work on the B's too. So it's maybe most interesting in situations where the right thing to do might actually be different on the two groups.
Okay,
So,
I see.
Yeah.
Thanks.
Great question. Okay, so let's see about labeling bias. So labeling bias is similar kinds of thing, but it's not quite the same will happen. So here, ERM by itself will do the right thing until, like, we imagine that, some of these positives get mislabeled as negative. And it'll do the right thing until you've mislabeled enough positives so that actually the positive side for B, it starts looking more negative than positive, in which case, again, it'll just classify all of B as negative. The circles represent blue points that are now look green to us. And now above the line, there's 6 green points and 6 blue points. So, one more error and boom, it's going to try classifying all of B as negative. We don't want that. So that's what ERM would do. Now, equality of opportunity in this case will continue to lock in the H star and HB star. Actually, demographic parity will do that also. And that's because the probability, again, the probability that you're above the line conditioned on being blue stays the same, because our assumption is that the mistakes are equally distributed. And so the probability that you're above the line conditioned on that you're a positive example and we're not misclassified as negative still hasn't changed. Unfortunately, the probability of predicting negative giving you a true negative, that has changed. So equalized odds actually doesn't work anymore, and it'll mess up your classifier. And calibration will continue to force the classifier to favor group A and hurt group B to equalize these probabilities, and so will actually be worse than ERM that's unconstrained. So forcing calibration will actually force the classifier to start biasing itself, even when ERM by itself would do the right thing. And finally, if you put both of them together, equality of opportunity will continue to lock in the H star and HB star until the bias is so overwhelming it'll just classify everyone as negative, whereas the other methods won't. So kind of the takeaway message from this part of the talk is really that fairness constraints can have a different impacts on accuracy when training data is biased. And the particular ones that we looked at, the particular bias models and particular assumptions, equality of opportunity turns out to be the winner. It happens to be particularly helpful in all of these bias models. The other ones kind of sometimes help, sometimes hurt, and except calibration is particularly problematic because it's going to force you to take the bias in the data and push it into your classifier. Okay, so anyway, summary of this part of the talk. These are very stylized models of correct labeling functions and how data could be biased. But I think they give an interesting way to compare fairness notions by looking at how they impact accuracy. And these particular results, I think, give a nice motivation for equality of opportunity as just something that can help improve accuracy if training data is biased in these particular ways. But again, these are highly stylized models. Okay. So that's summary of part one. And now I'm going to switch to something kind of completely different. There's a lot we could still talk about, but yeah, I'm going to switch to something kind of completely different. And this is strategic online classification. And this comes from work at the EC conference this past summer called the Strategic Perceptron. It's joint with Saba Ahmadi, Hedya Behagi, and Kezia Nagita. And the setting here is, again, we're going to think of people applying for a loan, but now we're worried about not the decision maker, but worried about the applicants who are going to make themselves seem more positive than they really are because they really want whatever that thing is, the loan or being admitted to college. So, right. So we're going to think, let's think of, applicants applying for college and a different kind of bias. So we're classifying entities that will try to modify how they appear in order to get that positive label. They want to get accepted. And so we'll have a model where agents can modify their feature values at some cost. The challenge is going to be that it's going to be an online learning problem. And as you learn and modify your decision rule, the agents will change how they respond. So we will assume that it's public knowledge what classifier we're using to decide who gets accepted and who doesn't. And agents can then change how they modify themselves based on the classification rule. Okay, and this is particularly a challenge in the online learning setting because, you're going to be, as you change your classifier, the agents will change how they strategize. And so using game theoretic terms, this is a lot like online learning of what's called a Stackelberg leader strategy. Okay, sometimes this is called measure management in kind of management theory. It comes under names of Campbell's law or Goodhart's law. And the typical thing is if you have a company and you're trying to decide how do you, determine employees, promotion, and things like that, you're going to do it by maybe measuring some quantities. And once you measure some quantities, the employees will try to make those quantities look good, regardless of whether that's really what you wanted. These were just intended to be, features or things you're measuring. They weren't actually representing the real good things, but people will just try to change those. Okay, so All right, so here's the model. Be looking at binary classification. So same kind of picture as before, but now I really am going to focus on linear classifiers. The previous part of the talk, I was just using it as a kind of schematic, but right now, really think of linear classifiers, and I will be assuming that there exists a perfect classifier. So no more noise. Agents, the data points arrive one at a time. Our classifier makes a decision of positive or negative, and then is told the correct answer, and its goal is to minimize number of mistakes. We'll assume that agents have the ability to manipulate, to move themselves by a limited amount, either say in an L2 ball or maybe a weighted L1 ball, so it costs to change feature values, and their goal is to be classified as positive. I'll give some examples in the next slide. Think of agents of getting a benefit, a value of 1 from being classified positive, and a benefit of 0 from being classified negative, and having costs to move. Agents know the correct current classification rule. And so in particular, if the classification rule is deterministic, and it will be in what we're looking at, then agents can very rationally look at what they want to do. If they can, since they get a benefit of 1 from a positive classification, if they can move at a cost less than 1 and switch their classification from negative to positive, then they will do it. And they will do it in the cheapest way possible. And if they can't, then they won't do anything. They'll just stay where they are. So let me give an example of a kind of challenge that can happen. So this will be a two-dimensional example. Let's imagine that, so we have these 3 data points shown here. And let's imagine that it's not we'll look at the L2 ball case in a second, but for right now, imagine that they can move in the X1 direction, but not the X2 direction. So they can't change their height, but they can move horizontally by up to 0.9. Okay, and here's some data. And let's imagine we were running a typical algorithm. And let's take the perceptron algorithm. It's a very classic learning algorithm from the 1950s. Where you just start with one of the positive examples, and then you kind of update by adding or subtracting examples when you make a mistake. So if you're familiar with it, this will sound familiar. If you're not, don't worry, the algorithm is pretty simple. So you start with, say, the first positive example. Let's say it's this one. And you're going to make that be your weight vector. So this W here is your weight vector. And then this purple line is your decision boundary. So you're always using W.x greater than or equal to 0 as your decision rule. So to the right of that purple line is positive, less your negative. Now imagine this negative example comes along. Well, normally that'd be great. Hey, you correctly classified as negative. But remember, agents can move in their X1 value by up to 0.9. So this agent will actually move to the purple line. Think of the agent as, you know, what are these features anyway? These might correspond to, I don't know, test results that, you know, you could study extra for some tests. You're not really learning anything, but you're memorizing a bunch of facts that will improve your score a little bit. Okay, so you know, the person puts in a bunch of effort, spends a bunch of time memorizing lots of facts, takes the test, gets a higher score, and then is able to get in, even though they're really a negative example. So as the classifier, you let in some negative example, and you're not happy about it. So you subtract that example from your classifier to get this new example. But now the problem is this positive example, it's too far. That's a distance of 1. They could only, no matter how much studying he does, can't go that far, can only go this far. And so it's like, what's the point? So they just stay where they are. Like, what's the point in spending all this effort if you're not going to actually get in? So they stay where they are. They stay here. And then you find you made a mistake. Here's a positive example. I mean, later they do great, win prizes and all those sorts of things, and you didn't accept them and you're unhappy about that. So you add that back into your classifier and you're back to where you started. And then the same thing could happen over and over again. You keep going. When there really did exist a perfect classifier, if you had gone to this classifier, this would be a good classifier where this guy could study and get in, and this one can't. It's too far away. So there exists a perfect solution, but because you're bouncing around too much, you're not finding it. All right, so that's an example of what can happen here. And then the same thing, actually, let's think of a different example. where you again have the same situation, but now agents can move in an L2 ball of radius 0.5. So agents can move, like an agent here could move within a ball of radius 0.5. Okay, let's imagine that's the way the world is. Actually, same thing happens. You start here, and then this agent, it's distance 0.5 away, so it gets there. You go like this. Now this agent tries to go this way, but it's too far. That's root 2 over 2, which is bigger than 0.5. Can't do it, and so it just stays put. And then you're unhappy because you misclassified that. You add that to your vector. You get back here, and again, cycles indefinitely that way. Whereas again, this would be a perfect classifier where this agent could move at a cost less than 0.5, but this one can't. It's too expensive, so it stays where it is, and this would have worked. Okay. So this is just giving some examples showing how standard learning algorithms would fail here. Okay. So here's an algorithm that will work. We call it strategic perceptron, and it's an algorithm. It's a version of the perceptron algorithm that tries to be aware of this idea that people are going to manipulate. And I'm going to describe this in the case of L2 manipulation, so people can move in a ball of radius r. So I'm going to assume this radius r is known. So the sum radius r, and that's known of how far people can move. If you don't know r, you can do a binary search on it, wrapper around this, but let's just assume it's known. I'm going to assume there exists a perfect classifier, w star to x greater than or equal to 0 if there was no manipulation. So that's this purple line here. And because of that, that means that there is also a perfect classifier with manipulation. Namely, you take this and shift it over by r units. So if people can study and move themselves, by r, then you just shift this by r units, and then this person would be able to indeed reach the blue line, and this one wouldn't, and this would actually work and be a perfectly fine classifier. So if you knew what w star was, then the problem would be easy. You would take it and just shift that blue line, and you would get a perfectly fine classifier. The problem is we don't know what w star is. All we can do is try our learning. Okay. Now, I'm going to give a modified version of the perceptron algorithm, but just to kind of say what is it we want. So the perceptron algorithm, if you're familiar with the analysis, it's an online learning algorithm, and what it has to do is every time I make a mistake, it has to improve. It has to somehow learn from its mistakes. It has to make progress. And the way it makes progress is anytime it makes a mistake on some example x, it has to be able to update its weight vector using some, I'll call it x tilde, with two properties. One is that it has a positive dot product with the true w star, and the other has a 0 or negative dot product with the current vector that you have, w. That's what you need for this algorithm to work. Okay. If you're familiar with it, then that's great. And if you're not, just trust me, this is what you need for the algorithm to work. So let me say what our algorithm does. And basically, there are going to be 4 cases, and the first 3 are easy, and all the hard part is the last case. The last piece, not that hard either, but the last one is where the most interesting stuff is happening. So we're going to start in the usual way. We predict negative until we see the first positive example, x, and initialize w to be that x. There we go. Now, we're going to shift that over and predict using this blue line here. So this is our vector w. This is w dot x over the length of w greater equal to r. That's the blue line. And this is just, w dot x greater equal to 0. Okay, so we're going to use the blue line for our prediction. Now, if we make a mistake on a positive point x that's to the left of the purple line, like here, this point we can update directly. It's to the left of the purple line, so it satisfies this, and it was not manipulated. That's the true location of that positive. Why is that the true location? Because no one in their right mind would have put effort into moving and still get a negative classification. Remember, we're assuming that everybody has exact knowledge of exactly how much studying they have to do to get in. And so if you're not going to get in, why do the work? So they would just stay put. And therefore this positive satisfies this, and you can just use it directly for classification. Great, so that's an easy case. Now, what about making a mistake on the positive point that's to the right of the purple line, sitting somewhere here? Now, that's problematic because it does not satisfy the second bullet. Well, this should actually never happen. Why? Because if it's the point started here, it should have moved, should have studied and gotten to that blue line. Okay? And so we wouldn't be there. And if you started somewhere else, why would you move to there? It doesn't make any sense. So this should never happen. In fact, if it does happen, that means that your guess for R was too big. So you were guessing that people could improve by this much. And if you see a point there, it means, oops, your guess was too large. You have to reduce that guess. Okay, so that case 2 never happens. What about case 3? This is also an easy case. What about a negative example that's strictly to the right of the blue line? If it's strictly to the right, then that point was not manipulated because nobody would pay more effort than they have to. Therefore, it really is a negative. So if you flip it through the origin, the way you do with the usual perceptron algorithm, you'll get a point x tilde by just the negative of this, which is now a positive example and is to the left of your purple line. And so it has both these conditions. Okay, so those are the easy cases. Finally, let's get to the interesting case. This is a negative example that's sitting on your blue line. So this could have been a point that manipulated. And where did it come from? We don't know where it came from. We know it came from somewhere to the left because a rational agent would move in exactly perpendicular to the decision boundary because that's the cheapest way to improve. But we don't know how far. So here's what we're going to do. We're going to take that negative point, move it straight back to the purple line here, and then flip it through the origin. And this is just the mathematical formula for that. We pulled it back to the purple line and flipped it through the origin. We're going to update using that. So why that? Well, first of all, by design, it satisfies the second condition. It's on our purple line, so w dot x tilde equals 0. But what about the first condition? Well, we're going to use the fact, which we can prove by induction, that even if our weight vector w isn't correct, it always has a positive, or at least non-negative, actually it'll be strictly positive dot product with the true weight vector w star, and that's a property we'll maintain by induction. Because of that, we can now say, where did this negative example that we saw come from? Well, it came perpendicular to the blue line. I mean, that's the only rational agent. This blue line is really a hyperplane. You would move perpendicular to that because that's the cheapest way to become labeled positive. But we don't know how far it came. So it came somewhere between here and here. And notice we're moving it back farther, too far maybe, than it really came from. So we might ask, is that a problem? Is it a problem that we pushed it back more? Okay, so this point here is a negative example, but we pushed it farther. Well, here's the thing. So what we're doing is we're subtracting a larger multiple of w than we really should. And the question is subtracting a larger multiple of w than we really should, could that make this thing actually a positive example? And the answer is no. And that's because w has a positive dot product with w star. So if I subtract more w than I should, I'm only making the example more negative. So this guy, even though he started here, this negative, this point here is really a true negative. And so then when I flip it through the origin, I get a true positive and satisfy this. So that's the reasoning for why this part is okay. And then we can extend this result to the case of L1 costs, especially when you know what those costs are, and basically use the costs and the current vector to determine the direction the point manipulated from. The main difference is that in L2, agents will always manipulate perpendicular to decision boundary, whereas in L1, they will pick a coordinate, whichever coordinate gives you kind of the most bang for the buck, the most, I guess that's a US expression, the most success for the effort, the most, if you could, there's two tests you could study for, and there's one of them that'll be more helpful than the other, you just study for the one. Okay, that's more helpful. So you know which direction they did, and you can use that. For unknown costs, if you don't know what the costs are, then we're currently exponential in number of unknowns. Okay, so now let me just summarize that, and that'll be it. So we're examining a classic online learning problem, which is online learning of a linear classifier, but in a stylized strategic environment. Stylized because we're imagining that everybody has like the same amount they can move. We have this geometric representation that describes what they can do, and everybody knows the right answer, and they rationally decide what to do based on, hey, will that get me in or not? You know, in the real world, you never know, like, you know, am I studying enough to get an A or whatever? You never know that, right? So the agent's actions change as the classifier changes, and that can cause standard algorithms like perceptron to cycle. And we show you can derive manipulation-aware algorithms that succeed in the case where we know the manipulation costs, or at least not too many unknowns. There's a few interesting technical questions here, and I'm going to mention one of them, which is the following. I assume there was a perfect classifier. Now, normally, for online learning of linear classifiers, you can extend that to the case where there is a classifier that has small, what's called hinge loss. If there's a classifier of low hinge loss, you can get an algorithm that will make not too many mistakes, where the number of mistakes you make depends on the hinge loss of the best classifier. Now, you can also do that in this setting, but we only know how to do that in terms of the hinge loss of the best classifier on the points you actually see. And the points you actually see are not the true points. It's the points after manipulation. So you can easily get a bound in terms of the hinge loss of the best classifier on the points after manipulation. But we do not know how to do this in terms of hinge loss on the points before manipulation. And that seems problematic. You know, the problem is that doing it after manipulation is not so interesting, because maybe the way your classifier acted is making making this number really high. Whereas had you done something differently, that number could have been very low. You would really like to get a bound in terms of the hinge loss on the points before manipulation. And so then that we really don't know how to do. I guess maybe to mention one more thing in terms of, if you're familiar with adversarial machine learning, which is kind of related, the interesting case in what we're looking at is if you think of like the negatives and the positives, if they are so far apart that the balls around the negatives can be separated from the balls around the positives, then you know what? None of what I'm talking about matters. They can manipulate or not manipulate. There's no way that a negative could study enough to look like a positive. You know, basically you can separate them, and there's no way that, and so it doesn't really matter. The interesting case is what we're looking at is when these are actually close enough together that, yeah, the ball around the negatives can include positives. Negatives really can manipulate to look like positives, but of course positives can manipulate to look like they're even more positive. And so you stick your classifier over here, and now your positives can move up and the negatives can't. Okay, so that's really the interesting case for strategic manipulation. And that's where this kind of bounds in terms of the true hinge loss could be very different from in terms of the hinge loss on that points after manipulation. And I think it's also interesting to consider other manipulation models, classification functions, and so on. Okay, so that's it. Yep. And so let me end here.
Thank you. It's yeah. Maybe we have some questions from the floor or from the internet.
May I ask a question?
Yeah.
Sure.
Okay. Actually, I'm very interested in the setting that you mentioned, that actually strategic agents don't quite know how much effort they should take in order to make them look like positive. I'm interested in how can we model such lack of information in the of the agents, and and we can just discuss their manipulation behavior and consider the setting and how to counteract this kind of behavior.
Yeah, so I think that is a very good question. One possibility is to use, instead of a deterministic classifier, a randomized probabilistic classifier. And actually, there's been some work looking at this kind of thing in the offline case. But if you were to use a randomized algorithm classification, then like you set your threshold at random, with some probabilities, you have some probability distribution that you shift it. Then an agent, even if they know your algorithm, still will never know exactly how much, whether they'll be classified. So it's a little bit like, I don't know, instead of the teacher saying this is the cutoff for getting an A, it's like, well, I'm going to add a little bit of noise, so you never know, how much. Okay, we don't do that as teachers, but nonetheless, maybe you don't. Maybe it comes out that way though, but we don't try to. But anyway, that's one way to possibly model it. You could imagine allowing classifiers that are probabilistic. Another possible way might be to imagine that the points actually don't know where they are. That we're assuming that every point knows the classification rule and knows its current location. But maybe another way to do this is to imagine that each point there's a kind of a Gaussian maybe, and the point is given, it thinks it's like, maybe you don't really know how qualified you are, right? It's like you don't really know, you have an estimate. So that could be another way to model this problem. And that way you keep the classifier deterministic, but that could be a formal way to put uncertainty into the agents.
Okay, that's great. Thank you. And actually, I got another very small question about the setting too. That will the algorithm know the cost function of the agents? Is that a common knowledge?
Yeah. So in what I'm describing, I assumed that actually two things. One is that all the agents have the exact same cost function, and so that may be unrealistic, but and in what I described, that yes, it's known, and so that it was an L2 ball, and we know exactly how far they can move. Now, the exactly how far part that we can do binary search on. What we don't really know how to handle very well is what if there are costs to manipulate that depend, like this coordinate, that coordinate. Each coordinate represents a different thing they could do, and we don't know in advance which ones are easy and which ones are hard. That's a challenge that we don't know how to solve.
Okay, thank you. Thanks for your fantastic talk.
Any more questions? Can I ask questions? Yeah, come here. Hello, Professor Brown. Notice that in this part you mentioned you are focusing on the online learning setting. So whether can we design a no regret learning algorithm based on the awareness of strategic behavior of each data?
Good. So in the model I'm looking at here, we do not know how to get, that's kind of this last bullet point on this slide. We don't know how to get a bound in terms of the hinge loss, so kind of a regret type bound in this setting. Part of the problem is that it's a nonlinear model. It's a non-convex model in terms of how the agents react. So what do I mean by that? Let me just try to give an example. What do I mean? Let me just use this upper corner here. So imagine that here's an agent. Oops, didn't want that. Here's an agent, and here's maybe my classifier. And let's say the agent moves here. Let's say it's a negative, and it moves here. And now, what if I move my classifier slightly more? If I move it slightly more to here, all of a sudden that might be too far, and the agent will snap back and just stay where it is. So a little movement in what I do could drastically change what the agent does. And so that makes this very hard. Now, there has been some work. There's a paper out of the group at the University of Pennsylvania that considers a convex model. So there they assume, so I'm assuming that the agents want to be classified as positive. They get a benefit of 1 for positive classification, 0 for negative. And so that's the reason that if you move this thing over and they can't be classified positive anymore, then they'd rather do nothing, right? Because what's the point? They consider a model where the agent's benefit is a dot product with your weight vector. So if your benefit is dot product, that means it's not like you're trying to get above a line. You're just trying to increase your dot product. And so if I change my weight vector a little bit, that'll just cause the agent to move a little, to change how it's doing a little bit. So that's a convex model. And there they're able to get regret bounds. So it's really kind of this assumption about what the agent is trying to optimize and whether that has a nice kind of convex formulation, and in particular, if you change the classifier a little bit, will that change what the agent does just a little bit? Is there a way to basically in their formulation, you can view it, it ends up being a sum of convex losses. In our setting, it's just not. So that turns out to be the main challenge.
Okay, thank you very much.
Sure. Yeah, but there's a paper, it's Dong, Roth, I can't remember all the authors, but from a group at University of Pennsylvania that has some really nice work on that.
Yeah, Professor Chen.
Well, it's one more clarification. Can you hear me? Can you hear me?
Yeah, I can. It's a little hard, but go ahead.
I come closer. Can you hear me now?
Yeah.
All right. Yeah. Well, it's regarding the first part. So the knowledge you have about the data, I wonder the knowledge. Do you have any uncertainty about the knowledge? So what if there's uncertainty in the knowledge? Saying, for example, the percentage of say green dots mixed into the blue dots, right? It could be 10%, could be 5%, could be a bit more, could be a bit less. So if the situation is that you're unsure about the situation, and is there any strategy that it still, at least, recognize this kind of mixing of the other points into the region and get skill to improve the classifier, let's say.
Yeah, so actually, I mean, one good thing about these results, they don't require that the learning algorithm know the values, the betas, the news, those kind of things. They don't require, those are not known to the learning algorithm. The algorithm is just, ERM, just minimize, error on your training data subject to these fairness constraints. But the analysis only holds when really these various conditions are satisfied. So kind of on the positive side, the algorithms actually, like a different algorithm you could do is you could just try to reweight the data to undo if it's like underrepresentation bias, so some of the blue points didn't show up, well, just, give extra weight to the blue points who did show up to make up for the ones who didn't, things like that. But but these algorithms, they don't need to know any of that. The algorithm is just, minimize error subject to the fairness constraints. Now, the problem is that the analysis really depends highly on these conditions, like that for instance, that the bias is uniformly spread. So, for example, in the labeling bias model, I'm assuming that each positive example of group B is equally likely to have been mislabeled negative, equally likely regardless of where it is in feature space. You could imagine that maybe points closer to the decision boundary are more likely to be mislabeled as negative, and points farther from the decision boundary are less likely. That would be a different model, and that would, the results wouldn't hold there. So the results are kind of specific to some of these assumptions. And that's just, the best we know right now. So, yeah.
Any other question?
Yeah, can I ask a question?
Yeah, please, Ichi.
Yeah, so a very nice talk. Almost all my students tell me they can follow everything. So my question is regarding the fairness part. So can we forget this like fairness thing and just learn in the presence of the bias?
Yeah. So I mean, I maybe so you're asking like, so forget fairness. If I tell you this is bias, maybe we can just find an algorithm that works.
Yeah, exactly.
That's right. So I think for each of these, there are other ways to solve the problem. So if like in the underrepresentation case, it's particularly easy. In the case of underrepresentation bias, what you could do is for each blue point that shows up, just make more copies of it, and just weight it more. Just give more weight to equalize. That would work. And in the case of labeling bias, there are things you could do. So certainly there are other ways one could get those Bayes optimal classifiers. I think that's right. Here, really, our interest was just to say, you might not know if any of these biases are happening or not, and so you might say, well, these are fairness notions that you might be interested in potentially anyway. And here's extra motivation that if the data is biased, we don't know if it is, but if it's biased, they'll fix it in that way. But yeah, you're absolutely right that I think that there are many. And in fact, many of the these fairness notions to work, things have to be very particular. Whereas maybe if you just had a specific algorithm for it, you could handle a more general case. Yeah. So.
I see.
Yeah, I think it's a good question, but yeah.
Thanks.
Any more? May I ask you a question? Actually, I'm not supposed to ask question as a monitor, but it's not exactly a academic question. Yeah, but it's also like that. It's related to an exam. Like there was a national exam in 800 years ago in China. It's an imperial exam. So it's usually in spring. So it's around the examination the whole country, like students all over the whole country went to the capital to take the exam. Then what happened is like 61% get admitted, all from the south. Then the examination was cancelled, and another examination is taken in the summer. So in the summer, 61 students was admitted. It's all from the north. What can we make out of that from our study, academic study? Just any comment?
Yep. Yeah. I don't know. Very good. Great.
Okay. Yeah. No more questions. Just for fun. Okay.
Yep.
Thank you very much. Thank you. Yeah.
All right. Great.
Again next time.
All right. Great. Hopefully in person next time.
Right. Yeah.
Right.
Wonderful. Yeah. Thank
All
you.
right. Thank you. Bye.
Right.